Check, check. If I'm too loud, somebody just gesture at me aggressively to shut up. I will do the same to anyone else that's putting their mouth on the mic like this. Now I'm good to go, Matthew. It's recording? Cool. All right. Hi, everyone. Like half of you already walked in before we get started. But for anyone that is watching this after the fact, my name is Max. I am the team lead for the Spaceshot Subteam within the Terrapin Rocket Team, and this is our critical design review for our flagship mission, Cactus Bloom. We're going to be going over a few things today, but before we get started, I just want to give a preface. This has been a long time in the making. We work on year-long development cycles, and starting last academic year, we were already thinking about the design for this. We've had a lot of members, both old and new, who have been responsible for actually developing this project. You'll see a number of different people come up and talk about systems or system that they have had the opportunity to work on, and I'm very excited for everyone to get the chance to present. So kicking it off, a little bit about the mission, both Spaceshot as a whole and Cactus Bloom. The Spaceshot Subteam has the goal of making the Terrapin Rocket Team one of the handful of amateur rocketry teams around the world, collegiate amateur rocketry teams around the world, which are pushing for a space shot attempt, which means that you have a sounding rocket, which is crossing the Kármán line of 328,000 feet or 100 kilometers. Of course, this is a very long-term goal. This is not something that we can just hit on our first try, which is why we work up to it. So it is important, at least for me, while I'm here as team lead and for the team leads after me, that we're developing a framework for a team that actually can exist within the Terrapin Rocket Team and is capable of achieving this, and in the process, increase the rocket team's overall competency with high speed and high altitude, high powered rockets. Like I was saying, we work in a year-long development cycle where each academic year we start with a mission definition, actually defining what our goals are with that rocket. Those will come from the previous year's accomplishments or shortfalls, as well as from a long list of technical challenges which we expect to need to figure out in order to achieve the full space shot. We then develop that vehicle, launch it, and get a ton of data afterwards. We do this while also on the side pursuing a number of other smaller scale technical projects. And each year we continue to iterate on what we've done until we feel confident that we have a very strong understanding and technological capability to achieve the full space shot. For this mission, Cactus Bloom, we hope to further demonstrate the feasibility of the space shot vehicle architecture and correct from the technical and operational mistakes which we saw from our preceding vehicle, Dust Devil. We also hope to like we said earlier, further develop Spaceshot's competency with high-performance two-stage vehicles and evaluate several key subsystems, which will both be mission-critical and non-mission critical for Cactus Bloom. Our key driving requirements here are a maximum altitude of 50,000 feet, which is defined by our selected launch site of Argonia, Kansas, as well as a minimum recommended minimum altitude of 35,000 feet, which provides a good aiming point for us. We also, of course, need to make sure that this vehicle is fully recoverable. We will ensure that measures are taken to keep all people and property safe, and also are taking measures additionally to ensure mission success, mitigating risk where possible. The vehicle architecture should incorporate many elements of the full space shot vehicle, and this entire thing will be done for under $900, which is the real magic trick of this. Moving forward into a rough timeline here, October, which is where we are now, is going to be where we actually finalize the design and do the CDR, where you all are at the moment. And going into November, we are going to be doing revisions based on the feedback which we get from this event, and then actually beginning to order the parts and fabricate the vehicle. December, we hope to do an HEI and sub-minimum diameter casing test fire, which we will get more into later. In January, we will do a subscale flight in either a boosted dart or sustainer configuration, depending on the launch site which we opt for and motors that we have on hand at the time. And finally, the full flight will be happening in March at Argonia, Kansas launch site, alongside the test flight of the TRT's competition rocket, as well as our two-stage team. And we will spend April doing post-flight analysis and figuring out what elements we want to push forward into our next development cycle. A brief vehicle overview before we dig down into our subsystems. This is a CAD images, both external, internal, and internal of the Cactus Bloom vehicle. Altogether, it is about 2,200 millimeters, or a little over 7 feet tall. We have divided the subsystems, or the systems which exist on this vehicle, into 4 categories, which are the aerostructures, which is comprised of all external major supportive and internal components, aerodynamic surfaces, and to some degree, the recovery separation events. We have the propulsion, which is what makes the rocket go up. We have our avionics, which is the onboard and ground-based electronics, and the recovery, which encompasses event initiators, recovery event initiators, and the parachutes and recovery hardware. Looking a little bit closer into this, we've defined subsystems within each of these systems. Something you might notice is that things such as in the avionics system are actually encapsulated. Several of these subsystems are encapsulated by single systems, but we've taken care to individually classify each mission critical function, as its own subsystem, because that allows us to pay special attention into any interactions between these subsystems and better identify our risk. The vehicle will be able to fly in 3 different configurations. That is full flight, which is 2-stage, a boosted first stage and a boosted sustainer stage, as well as a boosted dart configuration, meaning an inert second stage, but a boosted first stage, and a sustainer-only configuration, so only flying that second upper half of the vehicle. Additionally, we expect to have a lot of flexibility with a range of different motors of the 75 millimeter class, which can fit into our booster in a much more limited range in the sustainer. Seen here is a brief ConOps chart of how that will actually work, but it is pretty simple. We burn the booster, separate, the booster goes off and recovers, the sustainer goes off and recovers, and that is pretty much it. There's also a coast phase in the full flight configuration before we ignite the sustainer, and that allows us to optimize the altitude which we get. But we're going to start off talking about our aerostructure system, which is what actually holds everything in place and does the is the aerodynamic surfaces as well that account for the flight. So,
hello, I'm Ethan. I will be talking about the aerostructures. Hi. Our vehicle is 2 stages. As Max said, it has a total length of 2.2 meters. We have a 75 millimeter booster and a 54 millimeter sustainer. Both stages will use 3 millimeter carbon fiber fins with a carbon fiber tip-to-tip. The sustainer is a sub-minimum diameter design with a carbon fiber motor case and body tube combination. Above the motor tube is a coupler, which is fiberglass, along with a fiberglass switch band. The nose cone will also be fiberglass with an aluminum tip that contains a recovery eye bolt. The coupler will extend 100 millimeters into the nose cone. Underneath the nose cone section, between the nose cone section and the electronics is a bulkhead that fits under the coupler. And then the threaded rods from that bulkhead will transfer the forces from an eye bolt that is not pictured into the forward closure of the motor. The motor case motor body tube combination will be carbon fiber wound with our filament winder. We will use Max HTE epoxy, which has a high glass transition temperature. We're planning 1 hoop layer and 3 1 hoop and 3 helical layers. The glass transition temperature is 205 degrees Celsius, and the motor burns at a lot higher temperature. So To avoid this from damaging the case, we will have a phenolic liner. To also characterize this tube, we will do a lot of testing, including 3-point bend, tensile test, static pressure test, and TG test, which I think we'll talk about more later. So the booster is a minimum diameter design with a fiberglass coupler and switch band. The booster tube will probably also be fiberglass, but it could be carbon fiber if we change it. That will also be filament wound. The motor retainer is Aeropack style design, and it'll be machined out of aluminum. And then we will have a aluminum transition also. The aluminum transition sits into the top of the switch band, right above the coupler, and it'll be bonded in. And then our recovery load will move from the transition through a threaded rod to the top eye bolt, which you can see in the recovery compartment in the middle.
Hi guys, I'm Olivia and I've been working on our stage transition design. And so basically the idea behind this piece is to sit in between the sustainer and the booster stage. And it consists of a conical shape that's congruent with the sustainer nozzle, as well as having sort of an outer shell. And the purpose of this is to hold the sustainer in place during the booster thrust. And so we plan on manufacturing this piece using aluminum, which the team already has available. And we will be making it either using the lathe or via CNC machine. And so we faced some challenges with the manufacturing of this piece. Specifically, we need to have tight tolerances to ensure that the sustainer is able to stay stable during the combined flight. Basically, this means that we need to have a tight fit so that the sustainer won't pivot when the booster and sustainer are flying together. And so once the pieces, the booster and the sustainer do separate due to drag, the booster has a much higher drag coefficient. And so this causes it to decelerate at a much faster rate than the sustainer does. And we have found that there are stability calibers of upwards of 4, which shows that the transition should run smoothly. And basically, this just means that once the stages do separate, the flight will be able to run at a smooth time.
Hello. My name is Jamal Allen, and I was responsible for the aeroelastic analysis. So what we used was a software called FinSim, which is commonly used in hobby rocketry. Although it's not completely accurate, it can give us a rough estimate as to the kinds of speeds and the forces that the rocket will experience while in flight. So these are the results that we got from the FinSim, and although we didn't use the strongest carbon fiber available, the results that we got were below the expected flight results from OpenRocket and the other softwares. So to mitigate that risk, we will have to strengthen the bonding with the fins, actually look at the kind of carbon fiber that we'll be using once that is finalized, and as well as take into account the tip-to-tip layup, carbon fiber layup that we will have for the final rocket once that's actually finished.
I'm Aiden, and I was working on the propulsion development and selection. And so to start it off, we had two initial requirements that included a 75 millimeter diameter sustainer or booster, pardon me, and a 54 millimeter sustainer. And so after that, we had several different trade space selections that we had to keep in mind in order to choose our motors, which were cost, availability, and performance. So the cost should exceed no more than 2/3 the budget for the final rocket. The motors typically take up most of the budget, and so this would be about $600 for the motors out of our $900 budget. And then we expect to receive like cross funding from other sub teams to perform like static tests of our motors to ensure they work properly and to ensure that they will give the desired results. For availability, we needed something that wasn't seasonal, so we could buy it at any time. And also, we needed stuff that was in stock, which was difficult to find. And then finally, performance. The combined impulses of the boosters and sustainers should be capable of propelling our rocket to at least 35K, but no more than 50K feet in order to stay within Argonia's requirements and legal issues. This can be adjusted by timing the sustainer ignition with the separation. So we had about like an 8-second separation from when the booster fell off to when the sustainer ignited. And this allowed us to get as close to our desired results as possible. And the motors cannot be sparky, as that is an issue in Argonia. They don't allow sparky motors. So we had several different options. We had the L1040, the L1420, and the M1500 for our boosters. And then for the sustainers, we had the K1100, the K250, and the K270. We decided on the M150 for the booster as we had that readily available for in our basically we had that already. We wouldn't have to spend extra money on that. And for sustainer, we had the K270 as it fits within our budget with the M1500 and the K270, which will lead us to about almost exactly $600 for these two motors. And it is a long burning, lower impulse, like average impulse motor, which will help us not exceed Mach 2. Both these motors are non-seasonal and available year-round, which makes them easier to buy, as we don't have to wait for stock to come out or pre-order them. And then this combination of motors will get us to our desired apogee range of about 45K feet and a speed of Mach 2. My initial simulation was done doing Open Rocket. Open Rocket yielded the following results. The important ones to note are the apogee, which said 45,700, which is exactly where we wanted to be, and then a Mach speed of 2.04, which is also exactly where we wanted to be. And then the thrust to weight ratio off the pad was 16.6, saying it will get off the pad and it will get off the pad fast. Then I did a cross check via RAS Aero. Open Rocket is prone to errors when it reaches supersonic speed, so above Mach 1. And to ensure nothing went wrong or the data was actually accurate, I cross-checked it with another simulation, which is not as user-friendly, but it yields better results. So as you can see, the apogee was also 45,700. Mach was about 1.97, and the thrust-to-weight ratio off the pad was 16.7. And so comparing these two, they actually yield very small percent differences, which is a good sign showing that they both are fairly accurate, and it's what to be expected when we actually launch the rocket. The only issues that I noticed were the stability at launch and stability at booster of the booster burnout. But these are no issue because they both fall within Argonia's requirements of at least a stability of greater than 1 caliber. And so then it's basically saying that we have the proper simulations and we know what our rocket is going to do in the air.
As mentioned earlier, we're using a head-end ignition system. Clicker. We're doing this mainly for reliability and because running a wire through fiberglass or carbon fiber in this case is unreliable and is easy to break. Therefore, we would have to make a whole new motor casing. We're using an kind of Aerotech inspired design. We kind of took one of their forward closures that were epoxied in We took their motor rings that we're literally just using the same O-rings from a reload kit. And we're taking the same surface area that is used to hold the epoxy in place, and we basically copy and pasted that. The main difference is adding the pyro bolt into the center, and then the threaded rods for motor or eBay retention. The reason we have a pyro bolt is so we can actually epoxy the motor ahead of time. We don't want to be driving, it's around 18 hours to Argonia with a motor with an igniter in it. That is not smart. To make this, it's all aluminum forward closure. We have thread lock in between the bolt and the head and ignition. We're using JB Weld to seal the igniter through that chamfer in the middle of the bolt. We have used this on past tests. This pyro bolt design, that was not the failure point of those tests. So we are pretty confident that it will work. It also holds up over pressure testing. Obviously, since we're making it from scratch and we have never tested it, we're gonna have to test it before trying to fly a rocket with it. So the main reason we are testing is for the thermal properties of the motor casing. Will this actually hold up to the motor burning? Will it just burn through? Will it hold the pressure? The HEI part, activation reliability, will having a igniter through that bolt be able to reliably ignite the motor, since we only get one shot of it when we're actually doing our launch. And then pressure loading, will it blow off the top? To do this, we are collaborating with the Aerostructure Subteam. As mentioned earlier, they're going to do a lot of testing on more of the actual motor casing itself with tensile tests and pressure tests and a bunch of other stuff there. We have a high glass transition temperature. This is about as high as we can get our hands on and still manufacture. We're doing material properties testing as mentioned. We're going to do hydrostatic pressure tests before all test flights and just tests in general. This is to make sure, since we're using, since they are epoxied motors, we don't use the same motor casing each time. Because of this, we need to make sure we can pressure test it each time. And then we're planning on doing 1 to 2 static test fires before we actually fly it in a rocket to make sure this is reliable and will not blow up the motor. No, avionics.
All right. So this is the avionics of the rocket. The booster and the eBay are very similar for what avionics they have, but the booster does not have, what the booster does have is a featherweight for GPS, a Blue Raven in Easy Mini, and then the batteries and screw switches for it all. The Blue Raven is the main for everything. It controls a separation charge and a cable cutter, and the Easy Mini has the backup charge and the backup cable cutter. The Sustainer has all of the same stuff, but it also has a run cam because Pixar didn't happen, and it's going to carry an SRAD U-Blocks for another GPS to test it out to see if we can build one. For the event trigger criteria, the booster's drogue will happen at apogee, and the main will happen at 1,500 feet, and that's the same exact thing for the Sustainer. The big thing that takes a lot of thought is the stage ignition for the Sustainer. We decided on, based off of the sim, the stage has to exceed 9,000 feet. It has to be less than 20 degrees off the vertical. And since it's in a coast phase, it'll be slowing down. Once it is going slower than 640 meters per second, that should be feet per second, it will once it's going slower than 640 feet per second, it'll send the signal through the igniter into the motor and light it.
Hi, I'm Jeremy, and I was in charge of getting the runtimes and power usage for the said avionics that we're going to be using. So on the booster, we are, as previously stated, running a Featherweight, Blue Raven, and Easy Mini using the available power usages found online. We were able to find the operating currents and minimum operating time we said was 5 hours to give us leeway both before and after launch in case we have to disarm or do any safety checks with the rocket. So for the booster power, we are going to use we need 130 milliamp hours of charge, which equates to roughly half a watt. And then let's see. Using those power usages, we can calculate the runtime. So the battery capacity changes for what component we're using. We are using 400 and 900 milliamp hour batteries because that's what we have most experience with. The 3.7 volts is also what we have readily available to help keep costs down. As you can see here, we have plenty of margin in our runtimes for all the components. This going up to the Easy Mini altimeter and the Featherweight. Similar with the sustainer, just this time adding the run cam and the U-blocks. The run cam does use lots of power, uses 135 milliamps. So we had to make sure we used a big enough battery to support that. As you can see, the sustainer power budget is 840 milliamp hours, significantly more than the booster. However, using the 900 milliamp hour battery, we're able to get 6 2/3 hours of battery life, which is more than enough for what's required during our launch.
So, hi, my name is Amin, and I'll be talking about our experimental GPS system. So, one thing that we have issues with is that the government doesn't like people having GPS systems that can accurately find position and velocity at really fast and really high, like really fast speeds and really high altitudes because of like commercial military applications or something. And so we have to figure out a way around this. So we have to basically develop our own in-house GPS system in order to bypass these limitations that are on most commercial units. Our plan for that is to use this GPS module right here. I guess that GPS module right there. It's a LEA 6T. This has the advantage of it being a timing GPS module, which means that it basically allows you to get complete raw timing data from the satellites that it connects to. Just for a little bit of background, GPS systems work by using a network of different satellites and then getting extremely precise timing data from each of them, and then matching those the differences in the time that it has from one satellite and a different satellite to triangulate its own position. By allowing us to get the exact timing data directly from the satellites, we can actually just calculate our position by ourselves, which means that it completely bypasses any of the internal solving. So the GPS module doesn't know how fast or how high it's going, and so it can't block us from getting data when we're going too fast or too high. In order to do this, this is essentially a long-term goal. For the actual Spaceshot vehicle, this is going to be something that's extremely important because we want to verify our altitude, and barometric altitude verification is extremely imprecise when you're going all the way to space because there's pretty much no air. And so we need to use GPSs or some other radio-based position and altitude verification system. The Cactus Bloom vehicle itself doesn't actually need this. It's going at a low enough altitude that we can use commercial GPS systems directly on board, but we do want to test this system so that future vehicles can use it. We do also have other backup plans for in case this system doesn't work completely. These are not going to be something that's going to fly on Cactus Bloom, but it is something that we will fly on future vehicles in case this doesn't work. These include ground-based range finding. This essentially means that you take a whole bunch of ground stations that you just set up, like you drive out really, really far and set up a radio-based ground station, which will kind of pretend like it's the satellite in space, and you do the exact same type of thing. So you give it exact timing data and allow it to triangulate its own position based off of the ground-based stations. The other option is to make a completely custom GPS module. This would bypass any of the restrictions because we're not selling it, and so we don't fall under any of those regulations. This is extremely, extremely complicated and also extremely, extremely expensive. But it is something that we can look into if the need arises. There are also commercial solutions. This is a really easy set it and forget it thing, but it's also crazy expensive. In fact, this is actually more than our entire space shop budget for this entire year, just the module. And the other way that we can do this is to do post-flight analysis of the IMU barometer and other GPS kind of GPS-based chips and taking all that information and amalgamating it into some sort of projected altitude. This is extremely unreliable and like not extremely accurate, but it is a simple thing to do that we know we can do.
Are you guys still not really looking into the Mosaic module based off of cost?
Yeah, that's kind of under the thing that I was mentioning about the commercial solutions like the Kate. The Mosaic module is something that's a little bit cheaper than a Kate, but it also needs to be combined with something like the Telemega or a different IMU and so or a different microcontroller, and so we'd have to have a lot more space to do something like that. But it is something we also can look into.
Given that it's a proven and slightly cheaper solution, it's probably one of the better options here. Have you guys tried to buy it through SBA at all, or are you guys mostly just limited to your OPRS budget?
I don't think we've tried to buy it. We haven't really looked into that too much. We just know that it's a lot more expensive than just making the LEA 16 module do its thing. This module that's on the screen right now is actually $12.
Okay, I would just keep it as a backup and maybe throw it on
Yeah,
SBA
sure.
and see what happens.
All right.
Okie doke recovery, which is important because I like rockets. So for the booster, it's a little bit heavier, so it needs a little bit of a larger parachute. It's 48 inches nylon strip, and it'll hit the ground at about 30 feet per second, according to the sim. And the sustainer is 36 inches, and it'll hit at 27.5 feet per second. The big thing that's yep.
Is your sustainer descent velocity with or without the motor? The loaded motor?
That it would be like after the motor is used.
Okay, so for your sustainer, you should be sizing your main so that if your motor doesn't light, it's still coming down at a safe descent velocity.
Yeah, okay. That's yeah. Someone writing that down. Thank you. Okay, so for the event initiators, like I said before, the Blue Raven handles all of the main. The Easy Mini is there for every backup. And the sustainers, so the we're using it's single set dual deploy, so we're using a black powder charge to separate, and then the main is opened up. It's bundled. It is bundled in like a Nomex blanket, and then once it hits main altitude, the cable cutter, which you can see in the picture there, blows, and that zip tie will break open, so the main parachute can open all the way up. We've used this before. We used it for Dust Devil's parachutes, and it's worked. And we used it recently for Jerboa's parachutes, and it worked. So we're very confident in the ability of the cable cutters. For the motor ignition, we're dipping EMATCH in BKN03, and we're putting prop shavings on it, because so that the EMATCH isn't quite enough to light the motor by itself, and that'll give it a little kick. We decided on 1 gram and 1.5 grams for both the primary and the backup, and for the sustainer and the booster. That is subject to a pop test. If it doesn't work, we'll up the numbers.
How are you making your charges? Like what style are they going to be?
It's going to be like the tube, it's like the tube with the hot glue, dog barf, and then black powder.
Okay, for everything?
Yeah, for all the charges.
Okay, cool.
I'm Vikesh, and I'm going over the operations and safety for the rocket. I want everyone to be safe while we're on the pad, so because I'm a loving and caring guy. All right, so first we have designations while we're on the pad. We highlighted 4 roles that are essential for when we launch on pad. The first role is a launch director, which directs personnel and oversees all integration. The second role is a launch safety officer, who monitors all operations to ensure proper safety and that the protocol is maintained. The third role is recovery and the avionics lead. They're responsible for ensuring proper integration and arming of avionics and recovery systems. And they also disarm all avionics and during the vehicle retrieval. And then the last designation highlighted is the structures and pyrotechnics lead. They're responsible for the safe and proper pad testing, integration, and disarming of the charges and or motors. The next thing we'd want to highlight as a safety procedure is the vehicle integration. The HEI bolt will not be inserted until the rocket is vertical on the pad. As well as that, the HEI bolt will not be physically connected to the Blue Raven with a screw switch after the rocket is fully assembled. After the rocket is fully assembled, sustainer deployment electronics are armed, and all non-essential personnel leave the launch pad. The booster electronics will be armed before the igniter is installed, and then the staging channel will be armed remotely on the Blue Raven. During the event of a successful launch, our vehicle disarm and retrieval process is refer to the range safety officer if the Cactus Bloom rocket has landed somewhere up high that we cannot reach. Then we will visually inspect for signs of active charges. This is so then the charges don't blow up in anyone's face. But in the event of an active charge, we will have to take care of handling it, and we'd have to prioritize disarming the avionics, which will trigger the charges if they're still active. And then we will have to move the vehicle minimally until all avionics are disarmed. This is to avoid triggering any really sensitive charges. And then finally, we will disconnect all batteries and remove any unfired charges, which then we could collect and retrieve the rocket. In the event of an unfired sustainer, we really do not want anyone standing in front of or behind the rocket, just for obvious safety reasons. We'd obviously also want to keep our hands away from the motor because it hasn't fired yet, and we don't want it to fire while we touch it. So in that case, we'd have to prioritize disarming the motor and then proceed to the nominal disarming procedures. And then finally, in the event of a ground misfire, we'd have to wait 60 seconds to approach the vehicle. So then the pyrotechnics slowly burn out. Using Bluetooth connected to the Blue Raven, we would disarm the pyrotechnics. And then after that, we'd immediately remove the igniter. If we're not attempting to relaunch the Cactus Bloom project, we would carefully disarm the electronics through first disarming the sustainer motor because of, it's a dangerous motor. And then we would second disarm any other avionics on the booster and sustainer.
Could you go back to your HEI arming slide? So do you only have a screw switch in line from your flight computer to your motor igniter?
As we were thinking about what would Andrew Bean say when we were putting this together, we were like, oh crap, yeah, we should probably put that in there. So yes, we will also be putting a shunt that's not reflected in the slides currently.
There you go. You know exactly what I was thinking.
Yep.
Also, another thing that I would make note of, you should arm everything in your sustainer first and then arm everything in your booster. In case the sustainer goes off, it will recover successfully. It's the same reason you turn everything on before putting in the igniter. So
that makes sense. Yeah, we're gonna flesh out these checklists definitely a bit more before we actually start using it, but we definitely have a good few months to do so.
Yeah, another thing. One thing Jim Jarvis does is he basically sets up his rocket at the rail, as it would be for flight, except the sustainer igniter is outside the rocket. So basically, run through your entire procedure with the sustainer igniter out of the rocket, make sure it doesn't go off, and then you can take everything down, put it back together, and rerun through it.
I like that. Okay, cool. That's great. Thank you.
Yep.
All right, well, I will be finishing it off, extending out that topic of safety and operations with everyone's favorite risk analysis. To do our risk analysis, we're doing a pretty standard risk matrix. Probability and impact are considered on a scale of 1 through 5. Low probability means, well, a 1 is the lowest probability and the lowest impact, and vice versa for 5. We'll be using a chart that looks something like this. Please don't get too scared by the bright colors. It's hard to look at, but it gets the job done. We categorize our risks by root system as well as the type. Any risk can be categorized into one of three categories, which is technical, cost, or scheduling. And given these risk matrices, we are able to then quantify risk and determine the priority in which we are putting on resolving them. I'm going to be talking about high and critical risk factors here, but feel free to comment on any risks which you think of that I don't mention or that I just don't get to that I did mention, because there's quite a few. So starting off with the aerostructures, you can see that of the 7 risks that we face, TN002 is the only one that falls into the higher critical category. This is our full list of risks. So you can take a second to scan over that or take a picture if you wanted to look over more. We'll also be sending out these slides afterwards for anyone that wants to take more time to look at it. But TN002 refers to the mechanical failure of recovery separation charges, which would result in the failed deployment of recovery hardware. Obviously, this is full loss of vehicle, which would be a pretty bad outcome. And for this reason, we have full dual redundancy of all of our recovery event initiators, and that's something that is built into our requirements. And we do that in order to mitigate those risks. On propulsion, we have a lot more risks that are present, 4 of which fall into the high risk categories. Again, big list, take a picture if you want, but we're going to be talking about 007, 9, 14, and CS002, which is CS is referring to cost, SC for schedule, and TN for technical, just to elaborate there. TN007 refers to ignition sequence of head-end ignition assembly failing to initiate sustainer motor, burn resulting in an inert sustainer stage. This would actually be not the highest impact, as our vehicle will be built around safe operations in the event of a no fire or misfire on the sustainer. However, it is quite likely because the HEI system is very experimental and they're known for being pretty dodgy. But we are mitigating that with our HEI static fire test campaign, which will help inform design modifications over the course of development so we can reduce that likelihood of failure. In the event of an improperly installed or manufactured forward closure, we might lose pressure or have a kaboomy in the sustainer, which would not be good. And so once again, HEI static fire will let us do testing and validation on that. An unqualified casing for the sustainer would result in the critical failure of that motor. And given that this is a in-house developed filament wound system with uncharacterized material properties, there's a lot of work, which is once again testing we are going to be doing to mitigate those risks. And the 4th risk here for propulsion that we identified as higher critical is a cost risk, actually. Additional testing requirements might necessitate the purchase of more motors. And given that we have a $900 budget and it costs about $600 to do one of each motor that we need, that is a thing that can be exceeded quite quickly. We've designed around affordable and available motors to help reduce this impact. And additionally, with cross-sub-team collaboration, which is primarily in the interest of the aerostructures team, we will be able to basically reduce the cost impact that we might have for testing. We also hope to get more budget, but we are not relying on that in program design. For avionics, we see 3 technical risks that fall under as being catastrophic and possible. And that would be 28, 31, 32. Take a picture if you want, you know the drill. And 3 of those would be our, first of all, our GPS system failing to send telemetry to the ground station, which could result in failure to locate the sustainer or booster after landing. When I say GPS system, this specifically refers to our mission critical GPS system, which is the featherweight, not the experimental one, which we'll be using. All of our avionics will be fully dual redundant. And we hope that that will mitigate any risks there. Another risk would be avionics system inaccurately detecting a recovery event threshold while the vehicle is being armed on the pad, resulting in premature activation of recovery events. This is both a danger to people as well as a danger to the vehicle. And if it were to pop charges, and so that is why we have been quite diligent about all of our protocols and procedures for such a finicky and volatile vehicle. The third avionics risk, which we higher critical avionics risk, which we identified, would be the avionics system inaccurately detecting sustainer ignition threshold while the vehicle is being armed on the pad, resulting in premature activation of. I said recovery events. I meant here to say the ignition of the sustainer. And we have protocols and procedures, once again, that will aim to reduce any risks of this. Finally, ending it off with the recovery system, we have two technical risks, once again, as catastrophic and possible for probability. First of all, if the cable cutter mechanism does not activate upon trigger, this could result in failure to release the main parachute. The parachute, while it is in the drogue state before it has been released by the cable cutter, reduces terminal velocity by an amount which helps with recovery, but not enough to actually ensure the safety of the vehicle after ground hit. So redundancy is our friend here. We will have two cable cutters, which are independently triggered one after another by our two different flight computers on each. Parachutes tangling is also another risk that we have, and this is one that's a lot harder to handle, as it's not something that you can really build around. It's due to aerodynamic effects that are pretty unpredictable. However, best practices with actually packing our recovery hardware, as well as focusing on proper timing of our recovery sequence, will allow us to try and reduce the risk of that actually happening. And that finishes it off. So thank you all for coming by. I'll be fielding questions now, or questions to anyone whose subsystem it pertains to. This is open to anyone on the Zoom. I think presently we only have a couple people on the Zoom who are here specifically for the purpose of reviewing. But for anyone that's watching this after the fact, you will also be sent this alongside a feedback form. That goes for anyone that's here now. There should be a feedback form sent out. So if you don't want to express any issues now, feel free to give it on later. But yeah, questions? Yes.
These are exclusively pertaining to recovery operations.
Mhm.
So the booster is going to just have one chute that deploys at apogee.
Yes.
And if it floats away, it floats away.
Can I actually ask you to repeat that again into the catch box so we get it on recording? There you go.
All right. Oh, I got two, both pertaining to recovery. First is the booster. Just to clarify, you have one chute deployed at apogee that will serve as the only recovery for that, or will that also be single step dual deploy?
Both stages will be single step dual deploy, same exact system, dual cable cutters, dual everything. And then, yeah, just the chute in the drogue state wrapped in the zip ties with the cable cutters, and then the main, which is cut afterwards.
And then with the cable cutters, you're planning to have those on the bundled chute free flying, correct?
Yes.
Yes. Okay. And those will be wired connected?
Yep.
Okay.
Long wire.
Long wire. Yeah. Okay.
And we have experience with that too, so we're pretty confident in them working. Yeah, if you want to throw that.
For the transition, are you guys planning to do a test run of that on Jerboa or some equivalent rocket beforehand, or are you just gonna send it?
So because that's aluminum and we have pretty good characterization of the material properties, we can do some FEA analysis of that. We might even be able to do some CFD there to get a better idea of what forces might actually be put on it if we are able to get that. But additionally, we are hoping to do a boosted dart test flight rather than the sustainer only test flight. That's really just going to depend situationally on when you're actually able to get to the test flight ready phase. But yeah, there's a number of things that we want to do to make sure that that transition is ready, and we intend to be quite attentive to it since that's a pretty high risk area. I don't know if that's gonna, let's do a little double pass there. Yeah.
Okay, you can do. I have a couple questions.
Sure.
Couple comments as well. So I have to leave. That's why I want to knock them out quick.
Cool.
Fencing, you can import custom properties. I don't know who I texted, but you can we have an email in the Rocket email. If you need me to send it to somebody, just ask Matthew or me.
Mhm.
But you can just custom import those properties because our Dragon plate is a lot, or at least the economy plate, what we have is like the properties are all different from what you guys did.
Yep.
Which is fine. But
Mhm.
yeah, import those. Do you know rail velocity off the top of your head or no? It also isn't that important. I'm sure you guys.
Oh, I'm doing volume now. You know what? I'm not doing that. Never mind. Do you know it, Aiden? 2000.
No, that's not rail velocity for sure. You can use Raz Arrow to do bevel angles because you guys have an airfoil.
Do we not have that off the rail? We don't. Sorry about that.
Ethan's getting it to me.
All right.
96.
Right now.
Be fine. You can use Raz Arrow to get bevel angles on the fins if you don't want to do like a perfect airfoil.
Beveling?
Like the same. Yeah.
Yeah.
Because they'll let you do the angles.
Yeah, we need to
It
do
might be
that.
useful. Maybe keep a backup COTS motor casing for the sustainer ready to go. I don't know if that's a.
Could you say that one more time? I'm sorry.
Maybe keep a backup motor casing, like a COTS casing ready to go for the sustainer motor. Just in case. I don't know how much it affects the rest of the airframe, but
It's like the internal diameter of the body tube is.
Yeah, we couldn't fit a standard motor casing in that, and that is the body of the rocket.
yeah,
So we
but
don't have
can
a.
it screw into the bottom of it so that it's not your filament wound casing isn't the one thing that's holding you back from launching.
Like our test launches, yes.
Yeah, we could look into making that less of like an impact for scheduling if we do need to redesign. It just, we have that would
something simple that just prevent so that like the filament wound casing. I mean, I have all the confidence in the world that it'll work, but like
it would
it's
have
the one thing
to
that holds you
be
back.
a different like just because we can't stick a motor casing in there, unless we could do an adapter maybe.
See if there's a backup plan.
Yeah.
Like just for testing, you could just put 8 mil for like just ignition testing.
Yeah.
So RCS sells casings, like filament wound casings. So we could use that.
Oh, perfect. Oh, I misunderstood your question. Yes, that makes sense. And we will look into that. If that's something we can accommodate on our budget, we will definitely have a backup motor casing.
Yeah, we just hate to do all the work and then like hit March and then be like, all right, time to go on break.
Yeah.
I already talked about modeling the blue ribbon extension board. Ground hit velocities are like 30 feet per second. It's a little high, but not that high. So just make sure the fin attachment's pretty good. I already talked to you about shear pinning everything.
Yep.
That might be useful. We talked about the arming sequence. Wiring diagram with all the additions we talked about would be great. Shunt, switches, all that stuff. Just that we know which order, like how it all looks and which order the stuff is turned on.
I agree. We should do a wiring diagram.
I wrote down sustain and recovery first, but you already covered that. And then Andrew had a question earlier about simulation settings in Raz Arrow.
In Raz Arrow?
Yeah.
What was the specific question? It was
what simulation settings we're using in Raz Arrow. Andrew, were you talking about like turbulent and the stuff like that and the surface finish and things like that?
Yeah, launch site settings, all that type of stuff. Also, your staging settings as well. I might have missed you covering that though.
To answer your first question, the velocity off the launch rod is 55 feet per second, and then for
That's really low.
That's low, but we made the rail length like 8 feet in the open rocket that Ethan has, and it was like 90.
Okay.
Yeah. For 2-stage more off the rail velocity is never going to hurt. And in that same motor case for your booster, you have some other pretty good options other than the M1500, which will get you faster.
Andrew, how long's the rails at Argonia when you guys went for the high power pads?
I have no idea.
Okay.
But you can just send an email to Corey and I'm sure he'll get it to you.
Yeah. They'll be about 8 feet at least. So hopefully.
Probably, yeah.
And then you talked about turbulent flow since it's 2-stage.
That's fine. In Raz Arrow sim settings, I think we're just the default. So I assume we should probably go back in there and maybe go for some better weather conditions on Raz Arrow.
There's weather conditions, and then there's stuff like the actual options. When you hit options under launch site, there's a few other options that you can check off depending on what type of rocket you have.
Okay.
If you read through the manual, yeah, Chuck Rogers has some suggestions for two-stage rockets on which settings you should use.
You hear that, Aiden? That's your job. Any other questions, comments?
Let me get out of your hair.
Thanks, everyone.
Could you go back to the slide with the interstage?
Dang. Who said you get to be a presenter and a commenter? I'm scared of these questions.
Okay, so that looks like it's just a Boolean with the nozzle taken out of an aluminum chunk, right?
Yeah, is that how they did it?
Okay. How are you planning on getting the tolerances to do that? Unless you're just gonna like make it slightly oversized or something.
I think something that we need to revisit and something that we honestly talked about last night, I'm not gonna lie, is this is just not a really manufacturable piece. We're not gonna be able to make that on a CNC. I think that we want to keep the same form factor. However, this would be ideally manufactured in two pieces that could screw together, if that makes sense. So having that like ring around the side go onto that, thread lock it in place or something. And
yeah, if you have the cone and the ring separate, it would be really easy to manufacture. Also, if you just make the outside, like the parts that go around the outside of the nozzle, just a little bit wider, that would also make it a lot more manufacturable because that means you don't have a really tiny little ring at the very bottom.
Yeah, and something else that we also discussed too was having a boat tail wrap around the nozzle, the part of the nozzle that actually sticks out, and then having that divot there where the nozzle goes into place be more of a V than just like a straight line, I guess, if that makes sense. Is that, I don't know if I've described that well.
Yeah, I see what you mean.
Okay. Motor tube / body tube. It's the same tube. Yeah, because the nozzle sits on the bottom of the tube. It's on the tube.
The nozzle's epoxy to the tube, so it's like part of it too. I mean, the other thing is it would probably be better if you had like a little bit of space at the bottom of the nozzle so that as the nozzle heats up and expands or something, it doesn't seize itself into place and then you won't be able to drag separate.
Yeah.
Because it's or as it expands from like the aero like thermal heating, not from like the motor igniting, because obviously the motor is not going to be igniting that configuration.
I agree. I think that that's something that we're going to need to. I don't think that's going to be a huge risk factor right now, considering we're Mach 2, and I don't think we're going to get. Oh, I mean, there's definitely a thermal analysis that could be done on that.
I think
that's a pretty.
I wouldn't worry about that.
Yeah, I don't think it's a problem now. I mean, maybe that's something that we would become a problem down the line when we're like Mach 6 or something. But
this is also under boost where you're not going that fast. Like it's
Right.
not going to heat up sustainer lights.
Right. But honestly, overall, like I think that this there's a lot of attention to detail this time around with the transition section because as anyone knows, that was around for Dust Devil. That was a scarily loose upper stage on that booster, and there was definitely at least a degree or two of tilt in flight. So we really want to make sure that does not happen again. Which is why we're trying to prioritize tolerances and things that will reduce the actual flex of that during flight. But for the people that are commenting on this that are also members of the team, let's save it for a design meeting just so we could take any other questions. Anyone else?
A couple more comments on this thing. There's no reason you need the spike to go all the way into the motor like that. Just get rid of it. One thing people commonly do on conical interstages like this is a relief in the middle. So you basically are only contacting on the top and bottom of the cone. Because what can happen is when you have two cones like that, like in a lathe, right? When you're putting something into the tailstock, your Morse taper, it locks so it doesn't move. The same thing can happen here. So reducing that amount of surface area will still have a lot of stiffness, but you can, it'll actually release instead of locking into itself.
Right.
The other thing is the shoulder into the tube is very short. I would definitely lengthen that up because that will increase your stiffness a whole ton. Because right now it does, if that's a 75 millimeter motor, that's probably, maybe a 1/4 inch into the tube. You definitely need more than that. to get it basically pretty stiff.
Perfect. Okay. And also, Andrew, that's something something else about the transition I probably want to talk to you about after is how do you do high speed transition like aerodynamics for when you're separating from the booster for in the future. But for now, yeah, I think we're going to run with some of the advice that we've gotten here.
Yeah, I don't think your booster tip really matters after separation.
Okay.
Just let it do what it does.
Yeah. You got a question?
Oh, yeah. So I had a couple questions about the SRAD GPS.
I mean, you want to take this?
Okay. So first you mentioned the hardware that you're using for like the actual GPS signal. But what's actually like how is that data actually being logged?
So this actual module is not what we're going to be using. It's just the chip.
Right.
It's just that this module is like what we have right now. We're going to be making a custom PCB and then putting some sort of microcontroller on that. Right now, my plan is to just put some sort of ESP32 module. That way, it can have like all of the kind of stuff on board for it. So it'll have onboard flash and everything, and then that'll just log it directly to that. And then we'll just take this chip and put it on the PCB with the microcontroller.
Okay. And then the other thing is you use the power of like 7 milliamps for that chip, which is probably going to be a lot less than your microcontroller will consume.
Yeah,
not that it'll really be an issue for your batteries, but that is something to take into account.
Yeah, I did think about that when I was seeing that slide. When we actually do the like microcontroller stuff, we'll do another kind of study of the whole thing just to make sure that we're not going over our power budget. But I don't think it'll be a huge issue because it should take about this like a similar amount of power as like a featherweight, and that runs decently fine.
Yeah, right. Okay. Yeah, thank you. And then I also had a second question, just because I know it's something I think we've talked about on the Comp Rocket before with using easy minis now that we're going faster than Mach, I think. Have you guys considered a risk of like the Mach lockout and the easy minis firing prematurely? Because I think that's something we talked about before, right?
I mean, I'm pretty sure the plan is just to have the like time lockout. So it has a deployment lockout of a certain amount of time, and then we'll simulate that based on how long we think it'll take before we get subsonic. If that does become an issue, we can look into other like solutions.
Okay. Yeah, I just was wondering because I also I didn't see it in the slides and I didn't see it on like the risk matrix or anything. And I know that's a risk we've talked about.
Keep in mind for that, since you're using an easy mini, it only has 2 outputs. You have 2 separate if you have your sustainer lighting and your sustainer not lighting, and that changes the time. So just something to think about, because if your sustainer doesn't light and the timing is set for your sustainer lighting, your apogee charge isn't going to go until way later. So just keep that in mind.
I personally would have been inclined to switch over from easy minis to either just 2 Blue Ravens or a Blue Raven and something else. But I think that the Blue Raven is probably going to continue to be our primary.
Nothing wrong with 2 Blue Ravens.
Cool. Anyone else? Anyone on the Zoom?
Can you go back to your HGI slide?
What's the helmet? I keep changing my place. Oh, there we are.
So what is currently sealing your bolt?
You probably want to take this.
When you say sealing the bolt, do you mean the threads between the bolt and the actual forward closure? We're using thread lock. That's what we've used on all our motor tests, and there's been no damage.
So thread lock isn't a sealant, though.
Oh, sorry, not thread lock. Yes, seal tape. I am so sorry.
Okay, and you've used that on straight threads?
Yeah, just straight on the threads.
Okay, I would definitely try and pressure test that, just in a hydrostatic test, because water is going to come out of that.
When we had I don't know if you remember, like last year, our few like blow ups, it wasn't affected at all, and there was never any gas leaking from there. And we did pressure test it at that time, and it was fine.
Okay, all right. If it works, it works. It's really not much trouble to add an O-ring under the bolt head.
Yeah.
Like I would trust that a lot more than just Teflon tape.
We did do, I don't know. We did do like pressure testing at 1300 psi, and the seal tape was completely fine. There was a
Okay.
very small leak through the igniter leads, but that was before we had the idea of actually putting a like counter bore in there. I don't think it's modeled here, but we're going to put like a small counter bore in the bolt so that there's like a more hollow section near the tip, and then it'll be thinner, like that thin channel for the rest of it, and that should help with that.
We also
Another thing I've seen. Yeah, stripping the wires is another thing I've seen. I don't know if you guys mentioned it, but are you planning to use any radio beacons in this?
I'm sorry, what was that?
Are you planning to use any radio beacons?
Like, we can. I mean, we've had like pretty continuous disappointment with the cat tracker that we have.
Oh, really?
But yeah, I mean, it's not the best. I think that we could probably get like a general direction, but also it's so easy to just throw in with like a tiny battery or something.
Yeah. It's just a good backup to have.
No, yeah, I agree. I don't see any reason why we can't put it in there, and it's so little space, so that's fine.
It's worth noting our failures with it are probably a skill issue.
Oh,
yeah. Yeah.
Well, you can always go out into a field, have someone hide it, and then one person needs to find it. That'll teach you how to use them pretty well.
Yeah. All right. If anyone wants to participate in a beacon hunt, hit me up. All right. Anything else?
Yeah,
I probably
got a
missed this.
question.
Go ahead. Sorry.
So as far as the setup when it launches, I don't know if you guys discussed this, but should that be included in the simulation for my task? It's like a tungsten simulator.
I'm not sure I understand your question.
Like, should I take into account your initial setup when you're launching the rocket and take those initial values to account when I'm creating this simulation?
I don't think I'm fully following you, but you can Slack me and I can text you more about that after.
All right.
Cool. Andrew, you had something?
Yeah. So I might have missed this part, but it's a carbon case, right?
The sustainer, yeah, and then booster.
Yeah.
Right now we're planning on fiberglass, but we can do either way. I don't really think it makes much of a difference other than a slight weight change.
Do you have a cross section of the nozzle side of your sustainer?
Yep. Let me pull that up. The sustainer? Like,
yep. All
is
right.
this okay?
So yeah. So one thing to keep in mind, in a carbon case, it's a bit different than aluminum. Aluminum can take some heat. Carbon really cannot. So you have liner seal on the forward closure, but it doesn't really look like you have a liner seal on the aft closure. So I'd highly recommend adding a seal to the nozzle, because the last thing you want is gas leaking by your nozzle shoulder and just cooking the case and letting go.
Nozzle seal. Okay. Did you hear that?
Is that a nozzle or a phenolic disc or a O-ring?
This can be an O-ring in your nozzle shoulder that seals to the liner.
O-ring in the nozzle shoulder. Okay, great. We can definitely look into that. I think that we're gonna do like a lot of dedicated work just on this like setup with the submin, because that's definitely a lot of different ways that could fail. Something else to note is that I know we've talked about this, Andrew, but we've also we're pretty set on the idea that this is probably going to be a disposable system with the body, just because of like any heating and then structural effects that might have on the case, because that liner is definitely not going to keep it in great condition. But yeah, we I think that is something that I'll keep you posted in terms of like what we get from our tests.
Yeah, sounds good. What's your plan for keeping both the nozzle and forward closure in?
Keeping the nozzle and forward closure in epoxy.
So how are you doing that specifically?
Ethan, do you want to do this? Okay. Ethan has his hand up.
I kind of just modeled it after the way the Aerotech DMS motors are.
Okay, so you're making a big shelf basically.
Yeah.
The nozzle end seems a little small, so you may want a bit more epoxy there. But yeah, it's really important that you're getting a super good bond. You're not getting voids in there. I would practice this a couple times. Do make some scrap tubes and scrap closures, and just pot them in, pressure test it, see what you get. Make sure you're getting consistent results, and that you're getting really good bond strength there, because that is for composite motors. It's like a really big point of failure.
Cool.
Especially because your forward closure is so deep into your motor case, it's going to be difficult to get that glue joint, right?
Yeah, that is a possible problem. Do you think that there's enough space between the forward closure wall, like where the top O-ring is, and the tube? I don't know if Max, can you show on the slide?
Yeah.
The HEI slide.
Or the way.
Yeah, I mean, you guys are making a custom closure anyway. You can bump up the size of that liner O-ring, because that's what's really doing the work here. You're depending on your case being basically modeled around your liner OD, so that your liner is taking the pressure. So those O-rings on the forward closure aren't really doing a whole ton because it's all going through the liner. But yeah, I don't see a huge issue with that. I would just bump up that O-ring size so that doesn't get cooked as easily.
Perfect. O-ring size. All right. Anything else? O-wing once. Anyone here? Anyone on the Zoom? O-wing twice. Is there anything in that? Let me double check the chat real quick. Yeah. All right. Perfect. Okay. Well, in that case, thank you all for coming out. Really appreciate everyone's attendance, learning more about the rocket, everyone that had questions, or just showed support for the team. Yeah, we're gonna stop this recording now. To anyone watching this after the fact on recording, you are more than welcome to reach out to us directly or just submit your feedback directly to the form. Thank you for everyone that's participated in the design of the Cactus Bloom vehicle. Couldn't have done it. Is there someone in here? Sorry? Matthew Echo, no. All right, bye.
Bye, Andrew.
Good job, everyone. See ya.
Bye.
Thanks. You stop the recording, Matthew?